This discussion is intended as a supplement to the ZenBlue Intellisys module video. Here we will introduce the theory of machine learning for image analysis with an attempt to make you more comfortable using this capability as a tool. Machine learning has the capability to far exceed classical methods of image analysis in situations where signal-to-noise is a challenge, and the hope is that here we'll have a discussion that will explain why that is. To begin this discussion, let's start by defining the central concept of what is happening in machine learning. And to do that, let's first describe what we are accustomed to doing with classical image analysis. So in classic image analysis, the user provides software with a set of rules to apply to pixels in an image. These rules determine whether the pixel is part of an object and whether that object is valid. In our hypothetical situation here, we have an apple. And to get our software to acknowledge that this is classified as a valid apple object, we've provided a rule set. In this case, we said that the pixels within the apple need to be of some intensity, and that the object itself needs to be of a certain size. The key point here is that these rules are explicitly defined by the user. So how does this classical method compare with machine learning? The absolute key is that pixel classification here is done initially based on a criteria that would be software defined. That is, there is no explicit human definition of a rule set. Instead, the rule set is generated by the software and is derived from a set of training data provided by the user. As a result, the contents of the rule set are unknown. Using our apple analogy again, the machine learning the user provides the software with a series of images that contain multiple fruits. The human user conveys to the software, "This is apple," and "This is not an apple." The rule set for what objects are apples are generated by the training data, but they are generally unavailable to the user. The idea of applying unknown criteria to classify scientific data understandably makes people, including myself, nervous. Through this discussion, I hope we can ease those concerns and explain that while we may not know the exact criteria used in a rule set, we can know the types of criteria and how they're obtained, and hopefully lead us to an understanding that knowing the mathematical definition of the rule set is both unnecessary and impractical. So we've established that there is at least one primary difference between classical and machine learning-based image analysis. But how is this beneficial? The answer to that question is not obvious from our discussion so far, but in one word is context. The machine learning method of rule set generation provides tremendous power over classical image analysis because it takes into account the context of a pixel in order to determine whether or not it is valid. Let's consider how image analysis works versus our own vision for a moment to illustrate this difference clearly. Using classic image analysis, the very first step of determining if a pixel is a valid object is the intensity. As a person, you would never even consider what the intensity of a pixel or an object was in recognition. Instead, you would consider largely the surroundings of the pixel. Let's illustrate that this is true by looking at a binary image with only black and white objects. Classic image analysis falls entirely flat here, but the human brain does this remarkable feat of associating neighboring objects as a pattern to recognize this Dalmatian walking through a park. We can see the Dalmatian not by anything related to intensity, but solely based on its context. Let's literally look closer at an image to see how context works with machine learning and introduce the concept of a neighborhood. For classic image analysis, these two pixels are equivalent, and in the absence of any additional information, that makes sense. However, if we put this pixel into context, we can associate neighboring values as a property of the central pixel. We can call this slightly larger data set the neighborhood of the pixel. The intensity values of the neighboring pixels are actually best thought of as a property of the central pixel. This is a key concept here for machine learning. When we consider the neighborhood for the equivalent pixel, we may determine that these two pixels are not at all equivalent because the neighborhoods are so different. The power of considering the local neighborhood as a property of the central pixel is that we have more data points to compare pixels, allowing us to be both more sensitive and to discriminate with greater precision. In order to proceed with our discussion about machine learning and image analysis, we need to take a bit of a tangent to discuss the concept of the local neighborhood in image processing. Many of the typical modifications we make to an image are based on treating images as a series of matrices. This is a picture of a beautiful bougainvillea plant I kept over the winter and has recently bloomed. Of course, it's a very simple matter to blur this image, but what is happening to the pixel values when I do this? How are the pixel values modified to keep the image recognizable by largely preserving intensity and color, but to selectively destroy the image resolution? To understand this, we need to introduce the concept of a kernel. A kernel is a matrix of set values that, when mathematically applied to an image, changes the value of a pixel of interest in a manner that is determined by the local neighborhood of that pixel. The output of the operation replaces the original value of the pixel, and the process is repeated for each pixel in the image. Depending on the type of kernel, the results can dramatically change the image. For my bougainvillea picture, I applied a Gaussian smoothing kernel from within the Zen imaging software. The values of this smoothing kernel can be seen here. How this kernel was applied to the image in a sequential manner can be seen in this animation. Notice that the kernel uses intensity data from a local neighborhood of size matching the kernel size, but the modification of the final product only occurs to the central pixel. In more detail, here's what's happening on a pixel-by-pixel level. The neighborhood acted on by the kernel is always the same as the size of the kernel. The top left pixel value of the neighborhood is multiplied by the top left value of the kernel, and so on for a full 3x3 neighborhood, or whatever the size of the kernel. The resulting output becomes the new value of the central pixel. Note that only one of the pixels in the neighborhood are modified. This process is then repeated with the kernel shifted by a single pixel as shown in the previous animation. Should you be wondering, during the sequential steps of applying the kernel, the original image data is always used, not the newly derived pixel value for the adjacent pixel that we have just determined. The result of this smoothing kernel is the central pixel becomes more like the values of the surrounding pixels. In this manner, you could say that the image processing makes us sensitive to the context of the pixel of interest. Let's try and make our way back to machine learning now. How would this image processing be used to help in the classification of pixels? Well, let's look at a more advanced example of the application of a kernel to answer that. Here we have a small section of 3 independent images. At first glance, these local regions appear to be different from one another with no real equivalency. If we attempt to group the central pixels by similarity, this is difficult because the intensity between A and B is very similar to the intensity between B and C. If we had to group these pixels into 2 groups, it would be logical to associate A with C, as the two have closer values of their intensities. However, if we apply a filter to these neighborhoods, in the case of an edge detection filter, we draw out similarities that are not so apparent initially. Applying a horizontal edge detection kernel reveals a sort of line running through the center of neighborhoods A and B, but not so much in C. Now, if we were to be asked to classify pixels in these neighborhoods as similar or different, we can use this filtered image as a basis for classifying the central pixel of neighborhoods A and B as being similar. So what does this have to do with machine learning? If you recall that at the beginning of this discussion we outlined step 1 of the process as a generation of a rule set. The example we gave was the user input of several types of fruit and the apples identified by the user as being a common group. Now, instead of apples and plums, let's consider our 3 neighborhoods and our accompanying central pixel. Here, the user has defined pixel A and B as being of the same type, and the user has decided that pixel C is of a different type. It is key to understand that this is a user-based decision at this point as to what pixels belong in what groups. Constrained by this user input, the software now searches for features that permit classifications of pixels according to the user-specified groups. This is the learning portion of the machine learning. In this example, given that pixels A and B are a user defined as being in the same group, we can see that it would be better to choose the edge filtered values as a method of pixel classification over the raw pixel value intensity, as pixels A and B are more closely related to these values and better discriminate from pixel C. It's important to note here that no changes are actually being made to the original data. These pixel values are being obtained from the edge filtered image, are simply determined and used temporarily for the purposes of classification. Now imagine, if you will, applying dozens of filters to each of these neighborhoods. Our software now has dozens of data points for each pixel and is free to pick and choose which of these does the best job of creating pixel classifications that the user has imposed with the training set. Moving from the theory to the practical, Zen image analysis software uses 33 features in a default feature set, and this can be increased up to 256 features to provide even greater power for this classification. Of course, the trade-off being that the processing time increases substantially as the number of feature sets is increased. The process of training the Zen image analysis software's machine learning module, called Intellisis, involves the user painting the image, providing groups of pixels that should be considered to be part of a similar group. For a complete explanation of the practical use of Intellisis with Zen or image analysis, please watch the companion video to this one. With that, we can conclude this talk on the basis of image analysis using machine learning. Enjoy your time exploring Zen.